Okay, welcome back. It's my pleasure to introduce Monika Kudlinska, who's going to talk about analogues of the Thurston norm in groups.
Great. So thank you very much to the organizers for inviting me. The conference has been really great. I had a great time. So today I'm going to start following the advice of Bruno with the theorem of Thurston. Okay, so Thurston. So for me, M is going to be a compact, oriented three-manifold. Okay, then there is a continuous map. Okay, so from the first cohomology of this manifold over the reals, that takes values in the non-negative reals. Okay, and okay, what's so special about this map? So this map is convex and linear on rays through the origin. Okay, so it's essentially a semi-norm. And moreover, so for any integral cohomology class, essentially this map is telling me, so it's measuring the minimal, so let me put this in quotation marks, complexity of a surface, okay, let's say dual to phi. Okay, so let me maybe make this a little bit more precise. So what do I mean by complexity? What do I mean by dual? So S is always going to be, again, a compact surface. But I'm not assuming connectedness now. So all my three manifolds are going to be connected, but actually S is not connected. But if I take the components S1 up to Sn, okay, then the complexity of S is just defined to be the sum of the negative Euler characteristics of the surfaces, but I'm ignoring things like spheres, for example. So if it has positive Euler characteristic, then I actually set it to 0. Okay, so this is from 1 up to n. Okay, so this is the complexity of S. Okay. And essentially what this theorem is saying is that when I look at an integral cohomology class, then this Thurston norm is computing the infimum of the complexities over all surfaces that are properly embedded in M and that are Poincare dual to this cohomology class. Okay, so S properly embedded in M and dual, so Poincare dual to phi. Okay, so we call this map the Thurston norm, but again, that's a bit of a misnomer. So in general, this map is going to vanish on cohomology. Well, it's going to vanish on cohomology classes that are dual to surfaces of non-negative Euler characteristic. But so unfortunately, this is probably going to be the only reference to hyperbolic manifolds in this talk. If M is hyperbolic, then the kernel of this map is just the trivial cohomology class. Okay, so in that case, this really is a norm. Okay, but in general, it might not be. Great, and then the other object that we'll be interested in, at least for a little while, is going to be the unit ball of this norm, okay, B of t. And again, so this is a convex polyhedron in H1 M of R. Okay, so why do people care about this object? So there are some very nice properties of this semi-norm and its associated norm, unit ball. Okay, and probably the most important one is that this Thurston, this unit ball, this polyhedron, parametrizes fibered classes. Okay, so what do I mean by this? So, okay, so there exists a marking of the top dimensional faces of the ball, okay, such that so an integral cohomology class is fibered. Okay, I'll remind you what that means in a second. If and only if phi is contained in the interior of the cone over the fibered faces. Okay, so recall we've already spoke quite a lot about this idea of fibering. So when I say fibered, what I really mean is that this manifold M fibers over the circle, and the fibers, okay, these surfaces are exactly the duals of phi. Okay, so it's this, when I say fiber, I really mean fibers over the circle. Great, so what does this picture actually look like? So I have my first cohomology and this polyhedron. Okay, so some of these faces are going to be marked, not necessarily all of them, and maybe none of them. And then I look at the cone over these faces, and then any integral class that lives in the interior of this cone is going to be fibered. And then everything else is not going to be fibered. Okay, so it's a kind of miraculous thing, but it happens. So that's one thing. It's not really going to play a big role in this talk, but this is what happens. Another thing that's kind of nice that I just want to mention briefly. Okay, and I should say, so this is also due to Thurston. So from the original paper where he defined the norm. The other thing is that actually you can read off some information about the manifold from this, from the norm and from the unit ball, and in particular, so B of t detects the JSJ decomposition of M when M is aspherical. And again, I'm being a bit imprecise here. So in fact, it doesn't suffice to look at just the norm of M, but actually you look at the norm of all of its regular covers as well, finite degree. Okay, so it turns out that when you look at that and you look at what the kernel is of all of these norms, you can detect what the JSJ decomposition looks like. Okay, and you could sort of see that here. So if M is hyperbolic, then you know the kernel of this thing is trivial, and then there are ways of making this an if and only if and all that kind of stuff. Okay, and this is a result of Boileau, Friedel. Okay, and then one more thing I wanted to talk about, which again I just wanted to mention because it corresponds to some of the other research, some of the other things that I'm interested in, and this is to do with profinite rigidity of groups. So it turns out that this Thurston norm, and in fact also the marking of the top dimensional faces that correspond to the phi-word classes is an invariant of the profinite completion, invariant of the profinite completion of the fundamental group of M when M is hyperbolic. M is hyperbolic. Okay, and this is, I guess, there was some results to this that kind of talk about this, but sort of this was really completed by Liu. And this is used to prove profinite almost rigidity of fundamental groups of hyperbolic manifolds. So this is a key step in that proof. Okay, so these are a few things that that make the object quite interesting. And so there are motivations, there are reasons why you would maybe want to get something analogous for groups. Okay, so groups that aren't necessarily fundamental groups of manifolds. And in particular, groups where you don't really have this nice Poincare duality. Okay, so that lets you take a cohomology class and identify it with some properly embedded submanifold or sub-object of the geometric model of your group. Okay, so the whole challenge is going to be trying to find these objects. Okay, where we don't really have a way of doing it a priori. Okay, so let's talk a bit about the combinatorial approach. Okay, so we're going to make some of this a bit more combinatorial. Are there any questions? No. Okay, good. So again, I'm going to start with an integral cohomology class. So M is still my oriented compact 3 manifold. And I'm going to take a, so it's now, I'm assuming, incompressible surface. So oriented surface dual to phi, okay, with components, so connected components S1 up to Sn. Okay, and I'm going to do the one thing that we can always do, which is cut along these surfaces. Okay, so by cutting M along S, okay, we obtain a decomposition of M, or really a manifold homotopy equivalent to M, which is a graph of spaces. Okay, so what do I mean? So the vertex spaces are exactly the components of M cut along S, so it's the complement, and then the edge spaces, so edge spaces are the components of S. Okay, and then adjacency in this graph, so adjacency is determined by inclusion. So in the sense that the components of S are now boundary components of these complementary submanifolds, and then if some component is the boundary of one of these 3 manifolds, then that edge is adjacent to this vertex. Okay, and so we have this graph of spaces. We can take the geometric realization of this graph of spaces, and then we can take the fundamental group of that. Okay, and so what this gives us is that the fundamental group of this 3 manifold, okay, splits as a graph of groups. Okay, so this is all very standard, but I just wanted to maybe draw the link between the manifold world and the group world before we actually completely abandon the geometric setting in a second. So you should really be thinking of these graph of groups as fundamental groups of these graph of spaces, if this is not something you're familiar with. Okay, so there's a graph of groups, which I will denote by Blackboard font X. And this graph of groups has some special properties, which I'm going to encode. So first of all, the underlying graph X is a finite graph. Okay, so that's kind of important. So secondly, the edge groups, which are just the fundamental groups of these surfaces, are, okay, of type F. So I can say this now after Claudio's talk. So in other words, they have finite classifying spaces. Okay, so here it's obvious because the classifying spaces, well, in case these are just, yeah, maybe I should assume that these are not spheres. Okay, so these are not spheres, not, yeah. Okay, these are not spheres. So the edge groups are of type F. And then the last thing, which is also important, and is to do with the fact that this surface is dual to this map to Z. And yeah, so other thing I should say that I'm now really thinking of this H upper 1 as I'm identifying with the homomorphisms from pi 1 of M to Z. Okay, so I'm really thinking of these cohomology classes as just homomorphisms from the fundamental group to the infinite cyclic group. Okay, and so the edge and the vertex groups are so identified with subgroups of the kernel, okay, of this map to Z. Okay, this is duality. Okay, so let's just quickly do an example of what happens in the case where S is connected, because then it's actually quite nice and easy to see. So if S is connected, okay, incompressible dual to phi is non-zero. In particular, so S is non-separating. Okay. And so we can sort of divide this up into two situations depending on whether we're looking at a fibered class or a non-fibered class. So if this cohomology class is fibered, so S really is just the fiber of a fibration over the circle, then we've already seen this picture drawn many times at this conference. Okay, here you have some sort of, okay, I drew this as a just sigma cross I, but really there's some interesting homeomorphism of this surface happening here. Okay, and so the graph of group splitting is just a loop. The edge group is the fundamental group of this surface, or can be identified with, and the vertex group is, again, the fundamental group of the complement of the surface in M, or some tubular neighborhood, which really is just S cross the interval. Okay, so it's just S cross the interval, so it really is just the fundamental group, isomorphic to the fundamental group of S. Okay, and then the other thing that I wanted to point out is that the kernel of this map really is just the fundamental group of this surface. Okay, there are no other loops living in the kernel. And then, so what's really interesting me more than this situation is when this is not a fibered class. Okay, this is for the purposes of this talk, this is actually the interesting situation. And again, so when you cut sigma along the M along S, you still get a connected three manifold. Okay, but now this manifold is no longer homeomorphic to just the product of S with the interval, just the normal product. Okay, so, but still we get this graph of group splitting where this is just one loop. This is the fundamental group of the surface, and this is just the fundamental group of the complement. But now I don't know as well as what this is. But I still know that this is a nice compact three manifold. So I still know that this group is of type F, has a finite classifying space. Okay, and then the kernel now. So it still contains the fundamental group of the surface, or after I should really put isomorphism after some identifications. But now the kernel is much, much bigger than the fundamental group of S. Okay, so the kernel now in particular is not even finally generated. Okay, not finally generated. So in some sense, the point is to understand the structure of these kernels when they're not just, they're not just coming from a fibration of a circle, but they're much more complicated. Okay, so let me, so now let's move away from manifolds and talk more generally. So let G be a group, and phi, now it's just going to be some homomorphism from G to Z. Okay, I will probably forget to mention, but I'm always assuming non-trivial. Okay, and then if Blackboard font X is a graph of groups splitting of G, which satisfies so these three conditions, A1 up to A3, that hold for these splittings of the three manifold groups. And I'm also going to make this assumption that's actually it's really not a big deal, but makes my life easier later. So, the underlying graph has one vertex. Okay, then the splitting is admissible. Okay. So these splittings, these admissible splittings, are exactly the splittings that are designed to mimic the splittings you get when you cut a three-manifold along some surfaces. And really, I should say, the splitting, and it's not just a splitting of G, it's a splitting of G that sort of also depends on this map to Z. So the splitting is a splitting of G, comma, phi. Okay. Yes. Oh, sorry. Is my writing really bad? Yeah. So the first one says the underlying graph is finite. The second one says the edge groups are of type F, so they have finite classifying spaces. And then the third one says, the third one is very bad. The edge and vertex groups are identified with subgroups of the kernel of phi. Is that okay? Yeah. Yeah, that's pretty bad. Okay, great. So are there any other questions? Good. So these splittings are designed to mimic the splittings you get from the surfaces. And so we can just define now the complexity of a splitting, the complexity of an admissible splitting, again, in a way that's supposed to give you back what you got from here. So here, the complexity of the splitting, I was really just looking at the complexity of the sum of these Euler characteristics of the surfaces. And so here, I'm just going to be looking at the sum of the Euler characteristics of the edge groups. Okay, and again, as I was doing there, I'm going to take minus, so actually to make this a positive thing. So these Euler characteristics I was non-positive, and then there's a little detail here that I don't want to spend too long talking about, but it's sort of to do with passing from spaces to groups where I actually need to weigh it by something. So let me tell you what this is. So this is the sum over all the edge groups in the splitting, in the graph of groups. And so Blackboard font XE is the group, is the edge group associated to the edge E. And then this this G of E is an element of the group G, which is the edge element. Okay, so it's a thing about graphs of groups where you also need to add to your group an element that corresponds to this loop here. Okay, so it's this loop here that these are the elements that I also need to consider, and I just need to see what happens to this element when I apply phi to it. Okay, so it's sort of to do with parallel surfaces. Yeah, it's just a little thing, otherwise things don't work out so well. Okay, good. So just to summarize, so we have these admissible splittings. The reason why we can only look at admissible splittings is, first of all, we need to be able to make sense of Euler characteristic of the edge group. Yeah.
So am I right that you're adding this factor because, for instance, if the class is not primitive, then you...
Yeah, exactly. So the graph of groups doesn't really see that.
Okay, because you want only one vertex, right? So,
yeah.
So for instance, if you have multiple surfaces, then you're forced to plot this. Okay, I understand.
Yeah, exactly. Yeah. Yeah, exactly. It's like, if I have, a bunch of copies here, and each of these is wrapping over the circle, I need to be able to take that into account. Good. Okay, great. So, are there any questions about the definition of this complexity? Yeah. Yeah, good question. So, so let me just, so if G is a group of type F, which means that I have this space X, which is the Eilenberg-MacLane space, the KG1, the classifying space of X that is finite. So finite dimensional, it has finite many cells in each dimension. Then the Euler characteristic of the group is just the Euler characteristic of the space X. Okay, and this is just some finite number, some integer. Okay, so that's the point. So we would be running into some issues if we had edge groups which didn't have these finite classifying spaces. So in fact, there's a slight weakening of this type F that I could have used here, but I don't really want to get into that. And for the family of groups I'm going to be considering, it won't really matter. Good. Okay.
Why does the issue of doing the max between that and 0 come up?
Doing the max between that and 0.
We didn't want to consider a sphere.
Yeah. So here, actually, all my groups are going to be, they're going to be, the geometric models are not going to have spheres. They're not going to have balls. They're going to be one-ended. Yeah. But there's a different, this is something I just made up. So there are variations of this that I'm sure you could use for other groups. Good. And really, in my head, I only think of aspherical 3 manifolds. So in some sense, some of these things don't matter so much. Okay, good. So I can now state the main theorem. So main theorem. Okay. And again, I'm going to explain everything after I state the theorem. And I think the only thing that will need explaining is actually these groups. So let G A of L be a right-angled Artin group, and this is a group that is defined and determined by some graph. Okay, and this graph I'm calling L here, and I'm going to assume that the graph L is connected. So this is exactly telling me that my group doesn't have any splittings over the trivial group. And then I'm also, so this is not really a big deal, but I'm going to assume also that there are no induced n cycles for n greater or equal to 4. Okay, and there's sort of a reason why this has to be true, but it's not really the point. So then there is okay, I'm going to be a bit fast. So there's a continuous function from the first cohomology of my group with real coefficients. That takes values in the non-negative reals. Again, it's convex and linear on race through the origin. Okay, and then such that when I'm just considering it, so I'm just evaluating it on the integral cohomology classes, so exactly the homomorphisms to Z, non-zero, then what this function is telling me is exactly the infimum of the complexities of the splittings, admissible splittings of my group, comma, the map to Z. Okay? So this, for the case where G is a fundamental group of a, let's say, a spherical three-manifold, this is the Thurston norm. Okay, this quantity here. Okay, it's just I had to rewrite it in terms of groups. Okay, so what are these groups that we're considering here? So we already learned something about right-angled Coxeter groups from Genevieve, and these are related. So if I start with a graph L, some vertices and edges, the right-angled Artin group associated to L is the group where I have a vertex, a generator for each vertex of the graph, and then the only relations are the commutators between the edges. So this is if and only if VW is an edge. Okay, so remember with the right-angled Coxeter groups, we're also saying that each of these generators has order 2. But here, these are torsion-free. Okay, these groups don't have any torsion. Good, and this is, and I'm going to call this RAG, right-angle Artin group, on L. Okay, and the isomorphism type here is exactly determined by the group L, by the graph L. I'm just going to assume these graphs are also finite. Good. Okay. The splitting is of G, yeah. So one of the conditions is that the vertex and edge groups are contained in the kernel of phi. Yeah, so this is why there's the dependence of phi as well. Yeah. Oops. Okay, so I think it's quite interesting to compare the strategies for the proofs of Thurston's theorem and for the proofs of this theorem. And it's sort of similar to what we saw yesterday, where there's a Thurston strategy, which maybe you could try and make work in this case as well, but actually it doesn't work, it's very hard. So you just have to come up with something completely different. So Thurston's strategy is actually quite simple. So essentially, it starts from the bottom down. So he starts with the function. He starts by just looking at the integral characters. Okay, so I'm just looking at evaluating each integral cohomology class on its complexity, which remember was just the infimum of the complexities of the surfaces dual to it. And he shows, so directly show that this function itself is convex and linear on raised to the origin, on raise through the origin. Okay, and then when I have a function like that, there's convex and linear and raised to the origin, of course I embed the cohomology with integer coefficients into the cohomology with the first rational, then real coefficients, and using the linearity and convexivity, I can uniquely extend this to a continuous function. So extend to continuous function on H1 with real coefficients. Okay. And one would hope that you could do this for groups. So if I just replace this complexity function with the complexity that I defined, maybe you could also sort of try to prove directly that this function is convex. But it doesn't, well, it might work, but I couldn't make it work. And so my strategy is kind of a bit back to front. But in some sense, it tells you a bit more. So it's a bit more enlightening in one way. And you'll see why in a second. So first of all, so remember, we started with we got this function, we got this norm, and then we got the unit ball of the norm, and that was an interesting object. Here, we're going to start from the end. So we're going to first construct a polytope. So a convex compact polyhedron in the cohomology of G with the real coefficients. I'm going to call this P. Okay. And whenever you have a polytope like this, this polytope induces a semi-norm. Oh, sorry. This is the first homology, and then induces a semi-norm on the dual vector space, the first cohomology. So now dual in a different sense, where if I just take a cohomology class, so then this semi-norm is just the supremum of the differences of 2 points when I evaluate them at this cohomology class. Okay, so for any 2 points in this polytope. Okay, I'm assuming this is a compact polytope, so this is actually really going to give me something finite. And you know, the picture is just I have some polytope, and then my classes, you know, I can just evaluate them and see what happens, see which one gives me essentially the biggest thickness. Okay, so sometimes this is called the thickness along P. Okay, so I'm going to construct a polytope that gives me for free a semi-norm, and then what I'm going to do is show that the semi-norm on integral cohomology classes is actually giving me the complexity. So show that this is equal to the complexity, so the infimum over all complexities of X, admissible, and splitting of GB. Okay, so now, in some sense, both of these stages are kind of hard, but there is already a good candidate for number one that exists. So I didn't actually construct a polytope. I used a polytope that already exists. And then the main bulk of the work of the paper was showing that this polytope, which is essentially initially defined through very unrelated means, actually has this nice relationship with the splittings of the group. Okay, so that was the main hard thing. Okay. Okay, so if you were hoping that you would have seen the back of L2 invariance, unfortunately that is not true, so let me remind you again about L2 homology. So in a sense, it's now a big thing in geometry group theory, or has become a big thing, so we're all talking about it. So thankfully, Genevieve defined all of these things, so I'm not going to read, well, I'm just going to remind you. So for now and forever, G will be a, okay, for now it's just a group. That's it. So the kth L2 Betty number of G is so denoted by BK2 in brackets. Okay, and actually remember when we were defining L2 homology, it was something to do with a space and a group action. So the space here is again, I'm looking at a classifying space. I'm actually not assuming it's finite anymore. So that's an important thing. It doesn't have to be finite, but I take a classifying space, I look at its universal cover, and then there's of course a G action on that. So this is the L2 Betty number that I'm computing. And what is this? This is just the von Neumann dimension of the kth L2 homology group of X tilde with the G action. Okay, and the important thing is that, okay, this von Neumann dimension, it's not necessarily an integer. Okay, so it can give you any non-negative real number and or infinity. So that's kind of not very nice. So X is a KG1. Okay, but then somehow things are nice. In some families of groups, and in particular groups that satisfy this thing called the Atiyah conjecture. Satisfies Atiyah conjecture, okay, which it's not really relevant for you to know what this is, but in this case, the L2 homology can be computed without having to learn a lot of analysis. So actually in this case, the L2 Betty numbers are just the ranks of just some modules. So here it's just the usual, just the normal group homology of G over some G module that happens to be a division ring. Okay, so here rank is really, you could even think of this as a field, and this will be a free module. The rank is what you would think. Okay, and this is what's known as the Linnell division ring. Okay, and in particular, and this is actually really the statement of Atiyah conjecture, these L2 Betty numbers in this case are integers. So we don't really have to worry about any of this nasty stuff. Okay, so I should probably be a bit faster. Okay, so we're going to be interested in certain cases. So I'm going to say G is L2 acyclic if all the L2 Betty numbers vanish for all K. And then it's of type FL2 if all the Betty numbers are finite. Sorry, I should have said Z, or I guess it has to be infinite. All the Betty numbers are finite, and they are eventually zero. So there is some finite number such that the L2 Betty numbers are all zero, L greater or equal to some n. Okay, so in this case, we're sort of in a situation like we had where there was a finite classifying space. So we had, with the finite classifying space, all the usual Betty numbers were finite, and there were only finitely many that didn't vanish. And so in this case, we can, if we're in this case, we can take the L2 Euler characteristic of the group, which is just defined to be the alternating sum of the L2 Betty numbers. So I is greater or equal to 0. Okay, and the first thing I want to say is that even for the nicest groups, well, I mean, this almost never happens. The L2 Betti numbers are never equal to the usual Betti numbers in general. Okay, but something cool happens. So when G has a finite classifying space, G is of type F, then the L2 Euler characteristic coincides with the usual Euler characteristic of the group. So in that case, the L2 Euler characteristic doesn't give you any new information. Okay, so this should tell you the reason why I'm introducing this L2 Euler characteristic is that we're actually going to be somehow talking about groups which are not of type F. And then it is really going to give us some extra information about this group. Okay, so the main point of all this so why is this useful? Why have I introduced these L2 Betti numbers? So this is a theorem. Oh, this is really, I mean, you won't find this theorem anywhere in the literature. This is a combination of quite a few theorems. So one of them is in a paper of Frieda Luck. Then there's in the thesis of Florian Funke. And then an important part of this that lets you talk about groups and not spaces is a work of David Kilak. So Kilak, okay, and this sort of joined up theorem is saying that if I have a group G, and my group G is L2 acyclic, type F, finite classifying space, satisfies the Atiyah conjecture, Atiyah, and there's I pick a homomorphism onto Z, so it's an epimorphism. Okay, then there exists a pair of polytopes, P and Q, in H upper 1 of GR. Sorry, H lower 1. Keep getting mixed up. So these are polytopes. So they're convex compact polyhedra, polytopes. Okay, such that, and I said this the wrong way around, so sorry about that. Okay, the polytopes don't depend on the map to Z, of course. So there exist polytopes such that for any map to Z, G to Z, epimorphism. Okay, when I evaluate, so I look at the seminorm induced by the polytope, and I evaluate phi at the seminorm. But I've got two, so I actually also look at the other polytope and take the difference of these two. Okay, and this is kind of strange. This tells me the L2 Euler characteristic of the kernel of this map to Z. Okay, so it's not the L2 Euler characteristic of G because that's just 0. That wouldn't be interesting. It's actually the kernel of the map to Z. Okay, and so, you know, of course, if the kernel is of type F, so this is essentially the case where phi is a fibered character, fibered homology class, then again, this is, well, it's still interesting. It's giving me the normal Euler characteristic of the kernel. But really what's cool is that you get this extra information. You get some finite number, essentially, in the case where the kernel, even when the kernel's not type F, not finally generated even. Okay, and it's sort of, yeah, and I guess I should have also said, yeah, maybe this sort of follows from this, but therefore, so the kernel, yeah, I should have said this before. The kernel is of type FL2. Okay, so it does make a sense to take the L2 Euler characteristic. So, yeah. maybe this should be here. And okay, so this is really strange. So you have these kernels, you can't really associate a normal Betti number to them. There's very little finite data that you can associate to them, but it turns out that the L2 Betti numbers are finite and they're giving you something new and something interesting. And now you would think that, well, we're on a good path because we have some quantity, but more importantly, we have semi-norms here. The problem is that the difference of these two semi-norms is not necessarily semi-norm. So really what has to happen is you have to live in this magical case where G is L2 exactly type F, has a TIA, plus there's some way in which you can arrange it so that you can take these P and Q where Q is just a singleton. Okay, in that case, this will always be 0 and we have a semi-norm. Okay, and it's very strange, but this works for some groups, and it in particular works for the groups I'm going to be talking about, but also it works for fundamental groups of aspherical 3 manifolds that are irreducible and with some other conditions. But so, for example, for a hyperbolic 3 manifold of finite volume, it's all of these conditions are satisfied, and this is really free to look. We're interested in this case for 3 manifolds. So. We have this for 3 manifolds as well. Okay. So are there any questions about this? Yes?
May these polytopes be non-symmetric with respect to reflection to the
Yes, yeah.
So second object is
Yes, yeah. Okay, so maybe this is really the last thing I'm going to have time to say. This is theorem. So again, that was the main theorem of this paper, but this is really the theorem where all the work is done. And so let A of L be a RAG, so right-angled Artin group, as in the main theorem. Okay, so let phi be a map to Z, so an epimorphism, epi. Then the L2 Euler characteristic of the kernel minus equals what we were interested in, so the infimum of the complexities of admissible splittings of the group with respect to this map to Z. Splitting of, okay. Good, so this is really the main meat of this paper, is proving that this holds. And in some sense, this is really the first type of result that tells you what this L2 Euler characteristic of these kernels is encoding, other than in the case of 3 manifolds where it's the Thurston norm. Okay, so in other words, this is really defined very, okay, maybe analytically or maybe even algebraically, but still there's very little geometry happening. And so it's a big mystery why these are finite and what these numbers mean. And for this class of groups, we can sort of understand that, or we can find some geometry, some geometric model which sees the L2 Euler characteristic of this kernel. Okay, and it's exactly the model coming from this admissible splitting, the splitting that realizes the infimum. Okay, so. Okay, and really, I mean, when I say infimum, so these are all non-negative integers. So this is realized by some splitting. Good. So maybe let me, in the last 2 minutes, let me just say why this theorem implies the main theorem. So as I was saying before, so we want to be able to apply the theorem of Friedel and Look, and then together with this theorem, to get a semi-norm. And so in particular, when A of L is a rag, so rag as in main theorem, we need to make sure that it actually satisfies all of these conditions. But this is no extra work for me. So in particular, this rag is seeing that it's of type F is very easy. Okay, there's a very nice classifying space for these rags. Then seeing that it's L2 acyclic, okay, it's also not too hard. And I've actually forgotten, so I think this is maybe Oken-Shrevey, or maybe Leary. So okay, this is kind of an old paper, but L2 acyclic is not too bad. And then the fact that it satisfies Atiyah conjecture is also, it's a result of Linnell, Oken, Shrevey. Okay, so it's actually, so the fact that rag satisfies the Atiyah conjecture means that, so this is a thing that passes to all subgroups. So in particular, and finite index overgroups, finite index subgroups. So this tells us that all virtually special groups satisfy the Atiyah conjecture. So in some sense, this is maybe not as restrictive as it might sound a priori. Okay, so this is, all of these conditions are fine. And then in order to actually say that we have a semi-norm in this setting, we say that also we can take these polytopes PQ such that Q is just a singleton. Okay, and this is again, so there's a paper of Oken-Shrevey where they compute these things, these P's, Q's. Okay, so this pair is really called the L2 polytope. So they compute these L2 polytopes for all rags. Okay, not just the subfamily that I'm interested in. Okay, and therefore you can apply this result. You get semi-norm. That semi-norm is computing the complexities, and you can extend it, and it gives you what you want. So I'm going to stop there. Thank you very much.